Alright, so we're going to review the print reading exercises, and this is all about location tolerances. It does, we will look at a few other things that you've looked at before as well. So we're looking at the bracket, page 434. By the way, you'll just check your chapter test questions online, okay? So I'll pretty much open that up so you can do that. All right, so looking at the 434. See if I can get all my technology going here at one time. It's a beautiful thing. So looking at the 875 diameter. That's a true position tolerance. Got the little symbol there. Positional tolerance is 0.028. And datum D then would be this description. Okay, it's an axis datum. Okay, because it's attached to this, which is a diameter. Okay, so it is an axis datum, and which is the 0.875 diameter. That's basically how you would describe it. Okay. The location dimensions enclosed by boxes and describe their purpose. Okay. So again, like I said, it's going to go back in time a little bit. All these print readings do. They kind of cover some of the basic stuff and fundamental stuff every time. So they're theoretically perfect dimensions. Okay, there's no tolerance. These basic dimensions locate. And you notice, it's a lot of times some of the sample drawings that we have in the book, they're all nice little perfect round, numbers, whole numbers, So here on this actual part, it's important for this particular part that it's 4.05000. So to the 10,000ths of an inch accuracy, perfect dimension. Okay, and then looking up this way, 0.9, 1.8, 2.7 to locate these. And then to locate this hole, it's 1.5 by 1.9500. Okay, so we would read that 1 point, or 1 and 900 and, or I'm sorry, get it straight here in a minute, 1 and 9,500 10,000ths of an inch is how you would read that. Okay, that's how you read that number. Or you can do it, digitally, 1.9500. Okay, which doesn't have as much impact on you when you're hearing it as saying 1 9,500 10,000ths of an inch. Okay, so the number of zeros in the decimal inch system gives you should give you pause, or give you, make your antennae go up. The more zeros you see, the higher the precision measurement is expected. Okay, and since it's a basic dimension, I know this sounds kind of funny, but it's really perfect. Okay, they're theoretically perfect dimensions, and the more decimal places you put on it, well, the tighter the perfection is expected. So it's just some kind of bracket, but man, they are really wanting the position of these things to be really, really controlled. The precision of our true position tolerance, the amount of our tolerance, is in thousandths of an inch. Okay, so it's 28 thousandths of an inch. Okay, how many hairs would that be? What did we say a hair was, roughly? Hair on your head. If you got curly hair, it's flat, but if you got straight hair, it's round shape, your hair is. You remember what we said it was? How many thousandths of an inch a hair is? 3. I know you're thinking, trying to come up with 3 thousandths of an inch. Okay, so 28 thousandths, 7 of those, 8, 9 hairs grouped together. Okay, so give you kind of a frame of reference. You got to come up with something, because we talk about these thousandths of an inch, and they're just, it's just a number, because we don't really deal with that. I didn't drive a thousandths of an inch to work today. You just don't talk about it, at work or normally or in your home or anything. Who moved my paper a thousandths of an inch? So it's not some kind of measurement or distance we think of all the time. So comparing it to a hair kind of helps. All right. Now, the positional tolerances for the actual produced sizes. Okay, so in reference to this, okay, to this dimension. So when we produce it at 0.880, the positional tolerance will be what? And then I'll give you the rest of them. Should be easy to do. Okay, now it's a max material condition. Say it's circle M. So what is max material condition? 0.880, right? It's the hole, so when the hole is at its smallest, right? So your positional tolerance can increase to what? You're allowed to increase as you move from MMC. So 880 is your least material condition, right? So what do we add to, how much do we add to our position tolerance? How much?
010.
Right, 10 thousandths. Okay? All right? We've done this a bunch of times. Okay, remember? So at MMC, if it's a hole, okay, at its smallest, okay, that's max material condition. All right, so that would be 0.880, what you're looking at, right? That's the hole at its smallest. All right. So at its largest, which is least material condition, am I saying that wrong?
I think so.
Oh, okay. 0.880 is least material condition. Oh, okay. Oh, okay. Just seeing if you're all. I was wondering when somebody's going to catch me. you know. But it is, MMC is at the holes at its smallest. Correct?
Yeah.
So that'd be 0.8 on your list, 0.870, right?
Yeah.
All right, so we start there. They just got, you know, it's kind of MMC at the top, right? On that list. No, MMC is on the bottom. Looking at your list on your print reading. Where's MMC? Which one? Holes at its smallest. 0.87 or 0.88? Which one's smaller?
0.87.
Right. So that's MMC. That's your MMC. That's your max material condition when the hole's at its smallest. All right. So since its circle M is next to the feature control frame, all right, so that means this tolerance applies at MMC. You are allowed to increase an equal amount with your produced size up to your largest, or LMC in this case. All right? So it goes all the way up to then what? What is our positional tolerance for 0.880? 0.038. Okay, 38 thousandths. Okay, so that hole is allowed to be located in a larger diameter tolerance zone. All right. Next, so the range is there. You know, you can figure out the measurements, but we go from 0.028 at 870 up. Okay, so as we increase 2 thousandths, well, we add 2 thousandths to it and just keep going up. So the list would be 0.038, 0.036, 0.034, 0.032, 0.030, 0.028, working your way down. All right, the next dimension, diameter 0.187. Over here, the little holes on the end of the bracket. There's 4 holes. We're using rectangular coordinate dimensioning, okay, for the pattern of holes, or for those 4 holes. And the multiple choice question there, which of the following most closely describes the positional tolerance? It's a single composite pattern. Okay. You've got 4 holes. See, it says 4 times. And there's a positional tolerance applied to the whole pattern. Okay, for each hole. All right, so it's a single composite pattern. Each position is to be considered singly. All right, the 0.156 diameter, which is the 4 small holes around the large hole. How many of these features are there? There's 4. Location dimensions is rectangular coordinate. And C, which of the following closely describes this one? This one would be called composite position tolerance. Okay, composite, as you have the actual pattern, and then you have the hole itself position. And normally, normal situation, you know, your pattern is a little bit larger, and then your hole itself is smaller. Control, tighter control. Okay. Now D, completely described. This is a long description. Okay. So you basically just start off saying the information, kind of what you have. It's a composite positional tolerance using rectangular coordinate dimensioning. All right, That's the first thing. The upper part of the feature control frame specifies a pattern locating control. Oh, okay, of 10 thousandths at MMC. And the pattern of features must lie in a group or as a group relative to datum A and D at maximum material boundary. Okay, so even though the circle M is not next to A, but I mean they're relative to datum A, comma, and datum D at MMB, circle M, and datum B. So it's related to A, D, and B, and D is at maximum material boundary. So D, remember, is a diameter. So at maximum material boundary of where that boundary of the axis would end up, okay, at maximum material condition, which is when the hole is at the position tolerance is at its smallest, right? We depart from MMC toward LMC. So when that hole, that large hole is datum, the axis of it is datum D. So when it is, 14 thousandths of an inch over to the right, let's say it's been produced and it's over to the right, then this pattern as a group of holes can be over 14 thousandths as a group. All right. Then the next thing, the lower feature control frame, is a feature relating tolerance at 2 thousandths relative to datum A. Okay, so perpendicular to A, right? Let's see. Where's A? Oh, A is the back of the part. So it's held in position. Each hole must be in position within the pattern at 2 thousandths of an inch diameter tolerance zone at max material condition. Very tight control, a whole lot tighter than this. So the hole is allowed to fluctuate quite a bit, 14 thousandths off of axis. And the pattern of holes is allowed to be within 10 thousandths of that, but each hole has to be within 2 thousandths of that. Okay? So our challenge is to kind of get a visual picture of that in our mind. Sometimes that's not possible. Sometimes you've got to actually sketch out worst condition for all three situations so you can kind of get a visual of where it would be. You know, you could use AutoCAD to do that. You know, draw a circle, show a center, draw a circle on top of that, representing one zone, draw your patterns, okay, and where they could be representing that 10,000 zone. See what I'm saying? Just kind of like what they've tried to show in the book. You know, to try and get a visual. It's so virtual, you know. It's not tangible. You can't, and we're dealing with axes here, which you can't touch on a part. Okay? We find an axis by figuring out where the hole is, measuring where the hole is. Okay? All right? So, composite positional tolerance has to be mentioned. Your upper part is at 10 thousandths MMC. Describe that. The lower feature control frame specifies feature relating positional tolerance at 2 thousandths relative to A, and the feature relating zone is free to shift. The feature relating zone, okay, 2 thousandths, is allowed to shift within the boundaries of the pattern locating zone. The feature axis must be within the boundaries of both zones. Okay, the axis. All right, next, 437. Okay, so we got 3 holes. And this one is a it's kind of funny word, 2 single segment feature control frame. All right, this one, the upper part of the feature control frame specifies your pattern of 14 thousandths MMC, where the pattern of features lie in a group relative A, B, and C. No modifier. Okay, so that means regardless of feature size. So no matter what size is manufactured, A, B, and C, this tolerance applies. So it doesn't care. All right, you want to put it in human terms. All right, the lower feature control frame specifies datums A and B. That datums A and B control the orientation of the alignment of the 2000's position tolerance zone at MMC. Okay, where the individual features must lie. Individual features within the pattern must lie, to be grammatically correct, or must lie within the pattern. Both the pattern locating zones and the feature relating zones must remain the same distance from the secondary datum. Okay, since B is the one common. Okay, A, of course, is perpendicular. Then B, which is from this edge, right, and basic dimension of 4.05. All right, 437. Mind benders. Some of this position tolerance stuff can be. All right. Why is there a separate feature control frame for the hole and counterbore? So we're looking at the counterbore, the .188 counterbore up here. Okay. So there's a separate position tolerance for the hole and the counterbore. The position requirements are tighter for the hole. Okay, so the hole listed first right here, and it's 7 thousandths. Doesn't really fully answer why there's a separate feature control frame, but except that we want to control the hole differently than we do the counterbore. Now, when you're talking about using a counterbore, what kind of fastener is going down in there? Why do we use a counterbore? What kind of fastener fits inside of a counterbore? Any idea? Okay, it wouldn't be a flathead screw. We'll X that one off. Okay, wouldn't be flathead, you know, which is countersink. All right, so what kind of fastener goes down in there? You may have seen them on various assembly, if you're putting things together, or any kind of metal furniture. A lot of times might have it in your, okay, a socket head hex, okay, socket head hex screw, okay, that you use an Allen wrench on, or a hex wrench on. All right, so a socket head, usually in the industry, in manufacturing or machining, machine assembly and whatever, that's common as dirt. If you got a counterbore, there's going to be a socket head hex screw going down in there that you use an Allen wrench on. Now, occasionally we might have a socket or a counterbore and put a standard old hex head down in there. But if you do that, the counterbore has to be very large, because you got to allow room for the socket to fit in there and have room to play. You know, if it's very deep, then it's got to be pretty large so that you can wiggle and get it in position and get it off. All right, in case it gets stuck. All right, so those kind of things have to be accounted for. But there is a standard socket head measurement for a type of socket size screw, socket head screw. All right, so what is doing the positioning on a counterbore shape? What is actually holding the part in position? Which part of that? The top dimension or the second dimension? The hole or the counterbore? What actually holds the part in position? Which one of those features? The hole. It's called the pilot hole, or the hole. Okay, and that's going to touch the sides of the screw. Some screws have a long shank on them, no threads, that is of a higher precision and controlled diameter, and that may be important for assembly of this part and actually touches the sides of the screw shank, okay, and holds it in position. So apparently, I mean, that's pretty tight control for a screw hole position. Okay, a pilot hole, 7/1000 in position, 7/1000. 2.5 hairs, roughly. It's pretty tight control. Now, you look at the counterbore, well, they made it 14/1000. Well, listen, when you make a counterbore hole in the machine shop, they're going to use a tool that's got a pilot shank on it, just a smooth bearing surface, and they've already drilled the hole. Then they'll bring the counterbore tool in and cut the counterbore. So they doubled it. They knew what position they needed for controlling the position of the part, and they just doubled the counterbore, you know, just for good measure. That's still pretty tight. 14/1000, that's less, that's 1/1000th of an inch less than a 64th of an inch. And counterbores are kind of run on 64ths. Okay? All right? So the critical thing here is the position of the hole. All right, so why is there one for the hole and a counterbore? So that we have a separate tolerance for the hole, and we're trying to locate the hole in a greater precision. B, we have hole and counterbore, and we're doing our little math. They're both holes, and they're specified at MMC, so we do have bonus tolerance allowed. So starting at the smallest for the hole, 0.187, your position tolerance would be what? It's right next to the circle M. Your positional tolerance for the smallest hole of 0.187 will be, since it's circle M, okay, there's no math required. Exactly. Okay, there's no math required there. It's not a trick question or anything. No math. Okay. Positional tolerance at MMC, okay, 7/1000 circle M. So as soon as you see the circle M, you know what your position tolerance is going to be at max material condition. It's next to it, okay? That calculates it automatic. Then, as we produce different sizes up to LMC, we're allowed to increase. So in your little chart there, it's going, first of all, jumps 1/1000, then it jumps 2, then it jumps 1. So you just add it to it, okay? So your next size would be 8/1000. Then for 0.190, it would be 10/1000. Then for 0.191, it'd be 11 thousandths. All right, so with that in mind, the Counterbore produced at 0.312 mmc, its position tolerance is, Lewis? Huh? It's right next to the little circle M for the Counterbore. Right there. It's in that feature control frame. It's what? 14 thousandths. You can say it.
Yeah, I just don't know if you're talking about the point.
Oh, okay.
I've got no meetings on the phone.
Oh, okay.
Yeah.
So, yes, the Counterbore produced size. All right. Of 0.312. Huh. Wait a minute. We don't have any kind of tolerance thing next to it, do we? Oh, okay. So we got to go down here. Let's look. Holes. 3 place. Plus 3 thousandths minus 1 thousandths. Ah. So this little funny little measurement here, funny little specification, made us look down in the title block, okay, our tolerance block for general tolerances. Okay, we do this to save space out on our drawing. You know, add a feature control or a tolerance control down here that's general. Okay, so let's look around. Oh, there's 580, 480. Gosh, a whole bunch of them do not have a local tolerance applied to it. Okay? None of them do. Okay, so we have to use this totally for our actual size tolerance for everything. So anyway, it's minus 1 thousandths, so it'd be 0.312, which would be the MMC of the hole, Counterbore hole. Then as we move toward the LMC and that little chart, we just add. So it starts at 14, goes to 15, 16, and then it jumps 2 thousandths, so 18. So, you know, your produced size, the actual part comes out of the milling machine, and some production person has got to check those. And they'll either do it a piece at a time, okay, or they'll have some kind of functional gauge that they'll just lay this part down on, and pins, dowel pins, or other types of precision manufactured rods could be inserted and immediately know if it's in position, immediately know what size it is. These kind of gauges that we check for sizes out in production are called go, no-go gauges. And they're just little rods, and on one end is one size and the other end is another size based on our range of tolerance. So we would have a special made go, no-go gauge that's 0.312 to 0.316. So on one end it's 0.312, the other end is 0.316, and maybe a half thousandths or something. And so if 312 fits, flip it over, stick the other end in, and it doesn't fit, okay, so we're good. You've checked it for its full range of sizes without using a measuring tool. Okay? 440. Interesting part. Double V block. Okay? And now, just a double V block used out in the machining or in the measuring lab does require a fair amount of accuracy. These holes that are on the side, do you have any idea? Now you got to kind of visualize what this thing looks like. It's kind of an L shape, and the top of it's got a V shape on top, okay, and then the side of it, the right side of it's also got a V block or a V-shaped groove on the right-hand side, okay? And we put round stock, round shapes in the top, okay? We lay round stuff in here and can measure it, okay? Or machine it. We can clamp it in, clamp this down, and then actually hold stuff in the V-block so that we can turn it and machine it or whatever we want to do, okay? Just helps hold something round in place on center. All right? With that in mind, what in the world are these 6 holes doing? What are they there for? What do you think? Why in the world drill a bunch of holes in it? You have any ideas? Just random holes, it looks like. Make it lighter. Okay? Is a thing. You know, it's one of the characteristics we're after. Alright? It can also be used, we can run a rod through there and we can use it to hold the V block in place. Okay? It can be used for that. It also makes, anytime you put holes, drill holes or punch holes in a mechanical part, okay, believe it or not, you make it stronger. Okay? That's why you'll see some bridge structural, it's got holes in it. Got holes punched in it. Makes it lighter and also makes it stronger. It increases the surface area, okay, for stresses to, instead of the stresses being all converging at one point on the beam or on the part, they're now, all the stresses in theory are at various angles to one another, spread around that surface area. You've increased the surface area, therefore spread the stress throughout the whole part more uniformly. Okay? Same reason why we put a radius, in this case, look at here, we got the funky looking little groove, radius, cut into the part. You would think, you know, you're looking at that and going, well, gosh, why would you want to do that? Well, if you got to fit something square piece up in there, it allows relief for the corner of the part that might fit up in there. And you also like quadruple the strength of that corner because you added surface area that wasn't there. Instead of coming to a sharp corner, now it's rounded and you have that much more surface area, which is, I mean, I said quadruple, it's actually probably more than that, because instead of a little point, now it's a whole surface. So all the stresses that you'd have where you're pushing this way and pushing that way and you're building up stress in the corner, stresses coming at a right angle to each other, they're now all at different angles around each other, all coming in at supposedly, okay, theoretically at right angles to the radius and to the circumference, okay, radial lines now of stress. So they're angled at different, and they're divided up, the stress is. So it's stronger. It's actually stronger by removing material. It's stronger by removing material. Crazy, isn't it? You just wouldn't ever thought that. You know, just looking at it, you think, well, put a hole in something, it's going to be weaker. Okay? Not where metal's concerned, or solids, you know. Now, if you take a piece of paper and punch a bunch of holes in it, that's a whole different story. It is weaker, you know, easier to tear, perforated. All right? So it doesn't distribute its load evenly. All right? So let's keep it going. We haven't gotten very far. Okay? So, how's it possible to have a 0 position tolerance? Because we put a 0 on it. All right, let's look. The 12, this one here. Okay, so this is a technique. It's possible to do it because, by golly, I can put a 0 on it. The 0 position tolerance just applies at the MMC size of the hole. So it basically says it's got to be right on. So there's no women in here. As we say in manufacturing or in the measure in drafting, a lot of times we say it's got to be dead nuts. Okay? Sorry, I don't mean to offend anybody. But that's what we used to use, you know. Out in the machine shop. Where's this got to be? It's got to be dead nuts. Okay.
What do you do if there's a, that's like work language or whatever, or lingo?
Oh no.
Yeah, what, you use it in the office or whatever, so what do you do? What do you say whenever,
It's got to be right on.
It has to be there.
Yeah, it's got to be 0. Okay. Anyway, some slang, you're going to hear it. So at MMC, it has to be at true position, 0 tolerance. Okay. So, very tight control. Obviously, this is working with some other kind of machining manufacturing process, and there's something fitting in there. It's very critical. Now, we look at these holes, and 50 thousandths, okay, 0.05, 50 thousandths of an inch. That's almost a 16th of an inch. So it's like, again, in human terms, well, I don't really care where those holes are, as long as they're kind of in this place. And then you look at how they're located. Uh-oh. Wait a minute. The book has been teaching us all along what goes with position tolerance. Basic dimensions, right? Basic dimensions. We don't have any. We got a bunch of, in fact, kind of weird looking numbers, don't we? So that's another indication, And I'm speaking a lot of here in terms of I'm out here making this part, and because that's what we're designing, that's what we're while we're creating the drawing, so it can be made. So I'm always kind of talking from that viewpoint, not from the designers, because as designers, drafters, that's what we're trying to do. We're making it for them to make for the customer ultimately. Okay? So, that's just kind of curious. I wanted to point that out. Now, it's also curious because this hole that's fairly precision as far as its position, it's also doesn't have basic. So, if it's a 2-place decimal, holy smokes. It's a 2-place decimal. Now, is this inch or metric? Yeah. Huh? It's metric, is it not?
It seems that way. I mean, I doubt it's 60 inches wide.
I don't know. There's some big machining out there.
Huh? Okay.
What does it say?
Inches.
Wow. Holy crap. That's another thing we say. That's a big, Mamma Mia, that's a big part. Isn't it? Huh? Wow. Dimensions are in inches and unspecified tolerances. Okay. How much does that thing weigh? Oh my God. 60 inches wide, 111 inches long, 5 foot wide block of steel. I don't know about that. You know, I think that's a mistake. I kind of do. All right. What else do we know about if it's a metric and it's following, it says it's following Y14.5, 2009. So what else do we know about metric and inch? What's the differences of the fractions or the decimals?
On the inch, you don't have a leading zero.
Ah, but on metrics,
You do.
you do. All right, what about the trailing zero? Trailing zeros, inch and metric. What do we do with them? Keep them on inch or lose them? Okay. Normally, we keep the zero, okay, on the front end if it's what? Inch or metric? Metric. Okay. So it's just the opposite. And then we chop the zero off. We don't have a placeholder zero as a rule. It's supposed to follow it. Okay. If it's metric. No trailing zeros. No placeholders. Okay. Let's look around on here. Ah, there's one there. Okay. But now this is a tolerance. I think that's allowed for that. Okay. But just dimension by itself, no. Say if it's true metric, it would be 1.6. Okay, so here's an inch drawing. So we're looking at that. Okay, so no leading zero, but we got trailing zeros. So, is it inch or metric? It looks like it's metric. I'm just going to say it's a metric drawing. They made a mistake. Okay? All right. I decree it. All right. Then B is positional tolerance at the possible produced sizes for that dimension. So let's see. It's a hole. So at 12.65, it'll be 0 position tolerance. Then as we move away from there, increase, then we're allowed to add. Okay. Then datum D. All right, let's look for datum D. I think I have this stuff memorized.
Top view.
Top view.
Top side.
There it is. All right, so it's the total width, which is a very odd number too, 60.32. Okay, so it's 60.32. All right, so since it's placed on a kind of a rectangular or standard kind of, you know, it's not on a diameter, then it's basically a center plane. So it's a datum D is a center plane. Okay, I'm going to need to. All right. Looking at the 44.45 dimension. Picking this this thing apart up here. It's a 0.12 position tolerance zone. Okay, and references datum D, regardless of feature size. Oop, right here. All right, and the meaning of the information is basically reading it. It's a center plane relationship since this measurement is referencing D. D is a center plane datum, so it's got to be, this measurement has to be on center with this one. So true position exists when the center plane of the feature and the datum center line, center plane line up. Okay, so when the two, this feature center and lines up with this, then it's at true position. Okay, and it's allowed to fluctuate within a 12 hundredths, I said 12,000, 12 hundredths tolerance zone. That's two parallel planes. Okay, and then that applies at MMC. So when this part, dimension, this feature, is at MMC. So it'd be, now it's an external feature, it's not a hole, it's not a diameter, but it is, let's see, an external feature. We still consider that, you know, so at MMC, max material condition would be when this is at its largest. I know it's a slot, kind of like a hole, but it's not really a diameter. Okay, so
You're referring to the wrong one.
I was?
Yeah.
Well, anyway, 445 is, that's what I meant. If we were looking at this one, no.
Right.
All right, 441, let's move on. Start moving faster, I promise. I'm going to change what I'm doing here, too. Rear. What? Oh, it's upside down. That's freaky, isn't it?
You put out of these sleep, yeah, that's a good way.
Watch this. What? Yeah. I don't know why it does that. Usually at the high resolution, it's the worst. Okay. All right, so we're looking at this one. Just got very little to ask about it. 0.290 counterbore over here. There's 8 of them. And are they rectangular or polar coordinate? So the holes, okay, let's see. Is it rectangular or polar? Really? Kind of looks that way. You got a diameter. And we've got an angle to locate that one. It's pointing at this one. There's 8 of them. The magic answer book, I think, missed that one pretty bad. Yeah. Wow. I don't know how in the world they thought that was rectangular. Because it's definitely on a radius and an angle. Okay, how many features are 8, and why is there a feature control frame? It's kind of these questions here, and the author's answers are just like You're like me saying, Andrew, what's your first name? Why is there, why is the same feature control frame for the hole in Counterbore? The positional tolerance for the hole and the Counterbore are the same. That's his answer. Well, okay. It just kind of answered itself. Okay. So, anyway, apparently, these are not as controlled. You know, it's 15 thousandths, and whatever kind of screw or attachments going in here, fasteners going in here, 15 thousandths must work for that particular type of fastener to have it the same. We don't need tighter control on the pilot. So, all right, 446. Moving ahead. Good old simple part. Huh? The femoral A and P saw guide standard. Whole bunch of questions though. Okay, so on the half-inch dimension, give the location dimension from datum B and the location application relative to datum C. So it's located, let's see, the feature is located 0.672, am I looking at the right one? Yeah. 0.672 basic, okay, from B. All right. and then on center plane for C, there's no basic dimension, and C is datum feature control is placed at the opposite end of the arrowhead, so it means we're to consider this measurement here, and it would be a center plane type of datum for position. Okay, and then at max material condition. Okay. All right. Explain the meaning of the information in the feature control frame. Okay. The half-inch diameter must be a true position within 14 thousandths diameter tolerance zone at max material condition. Related to A, B, and C at max material condition, or max material boundary, excuse me. C, provide the positional tolerance and virtual condition. Uh-oh. So, 0.505. We look down here, it's a 3-place decimal, plus or minus 5 thousandths. So, at 505, the position tolerance would be 24 thousandths, 0.024. Okay. And the virtual condition would be 0.481. And then at the half-inch, or 0.500 produced size, your position tolerance would be 0.19. Your virtual condition would be 0.481. Your produced size at 0.495, your position tolerance would be 14 thousandths. Okay, hole at its smallest. Your virtual condition is 0.481. Okay. chart, but so MMC of the feature minus the related geometric tolerance equals virtual condition. Okay. So in 710 on the opposite page, we start with 0.98. We add our position tolerance that's allowed. And I'm sorry, did I say add? It's an internal feature. So we subtract. Yeah. Okay. It's external, we add. So this is the internal. Okay. So 0.505 minus our position tolerance. 0.024 will equal 0.481. Okay. Next is the 3/8 24. Okay, now this is a threaded hole, so it's 3/8 major diameter. That's the hidden line you're seeing there, and the outside hidden line you're seeing here. 3/8 diameter, 24 threads per inch, which we don't show. We don't actually draw the little sharp V threads. We just represent it with hidden line. Unified National Fine is the form, okay? Unified National Fine, -2B, that's the rating or the way that it fits to the screw. Okay, this class of fit 2B. So B is an internal. You can tell that's an internal thread. Then 2 is the class of fit. Okay, so the location dimension from datum A and the location application relative to datum C. So your feature is located 0.28 from datum A and is on center plane here, max material boundary. And it's saying that's controlling the minor diameter. So that's the solid line or circle that's drawn there. Okay, which is not 3/8. Okay, it's going to be less. 3/8 is the hidden circle. Meaning of the information, this feature is controlled by a cylindrical position tolerance, okay, of 14 thousandths at max material condition. Okay, relative to datum B first. Okay, so where's B? B is here. Okay, so B, usually your first datum is when the hole is perpendicular to it. So that's usually what we list first. Okay, and then A in this case is listed second, order of precedence. It's the back of the part, and it has its own flatness control. So feature A, the feature is located 0.28 from basic, 2.8 basic from datum A and on center plane of datum C. And the feature control, reading it, is controlled by cylindrical position, 14 thousandths max material condition at max material condition with respect to B relative to A and C at max material boundary. 448. Oh yeah. All right, the 4 times 250. Okay, that's those little pins that are sticking out. It's thing almost looks like a brake pad. Give the location dimensions from datum A and the application and the location application relative to datum B. Okay? So the location dimensions from datum A. Datum A is the bottom edge. Okay? The lower features are located 0.652 basic from datum A. Right here. And then the upper features are 1.369 from datum A. So we add those two together. The lower features are 2.084 apart and symmetrical relative to the center plane defined by datum B. So whenever you place this feature, datum feature control on a dimension like that, okay, that means that we're talking about creating a center plane. Okay, the upper features are 2.135 apart, so they're just a little bit different than the lower features, aren't they? Okay, and symmetrical relative to datum B. The meaning of the information in the feature control frame. The features are located by a cylindrical tolerance zone of 20 thousandths at max material condition relative to B, C and A and B at max material boundary. Once again, looks like it's all out of order, all out of whack here. It's not A, B, C. It does not have to be. Remember, your hole, or pin in this case, whatever it's perpendicular to, datum it's perpendicular to, that would be listed first. The positional tolerance and virtual condition. So in this case, it's a pin. So it's when the max material condition would be when the pin is at its largest. So at 0.260, alright, your position tolerance is going to be 0.040. Okay, because you're going from MMC to LMC in this case. So at LMC, 0.240, your position tolerance would be 0.40. At MMC, which is 0.260, it'll be 20 thousandths. Your virtual condition for all three is 0.280. Just add them together. Next, 449. The old femoral bevel cutter. Okay. Here we have another threaded hole, and it's a countersink. So the location dimension for datum B here's datum B. Give the location dimension from datum B.
You're
It's
on
gonna-
1.9.
Oh, how about that? It was actually matching up. Got the same spec on there, doesn't it? That's interesting. 3/8 24, 449. All right. Thanks. Okay, here we are. How about that? So the location dimension from datum B is going to be 0.375. The feature is controlled by a cylindrical position of 14 thousandths at max material condition relative to A, B, and C at max material boundary. 13. Describe the use of the 2x individually placed below the feature control frame for the 0.193 dimension. Okay. This is also a countersink. Very light countersink. relief is added to it. So the note indicates that a multiple datum reference frame exists, okay, EDB, and that there are two separate datum features that need to be considered individually. Okay, so when we put this 2x individually, it means we're considering two of them individually from the other two. Part has 4 hole features at different angles. Okay. The 2 holes on the right side need to be positioned to different datums than the 2 holes on the left side. Here's E, 2x individually. All right. Coming in for a landing. 450. .422 dimension, diameter dimension. Up here. It's a large hole in the center. Location dimension from datum C is going to be 0.713, and it's on center plane defined by datum A. Okay, so an exact theoretical perfect measurement this way, and then regardless of feature size, center plane, whatever it's manufactured to, center plane here. Meaning of the information in the feature control frame must be a true position within a 14 thousandths diameter tolerance zone or cylindrical zone. Max material condition applies with respect to B. A at max material condition. Okay, so that'll be when that is at its largest, which we have to look down here. So it'd be +5, so it'd be 0.2135. When it's max material boundary, I keep saying condition on the datums. And datum C, which is for the left edge of the part. The positional tolerance and virtual condition. Okay, so it's a hole, so it's holes at its smallest would be MMC. So that's 0.417 using this tolerance block. Your position tolerance is 0.014, so we subtract because it's a hole. So our virtual condition is 0.403. Then we move up 5 thousandths. Position tolerance changes to 0.019. Virtual condition is still 0.403. Virtual condition, remember, is the combination effect of the tolerance of the position and the size of the part. By using virtual condition gauging, we can check for location and size of the part, particularly mainly for location, by using a pin located on center 0.713 and this at max material condition. And basically if this slides over that part, that hole, that pin that is, slides into the hole, that, and the pin is 0.403 diameter, it has achieved location. We know it's a good part. That over the full range of size and tolerance, its virtual condition is always going to be 0.403. So we know it'll fit over that 0.403 diameter rod that's on true position. It's a good part. So basically the inspector takes the part out of the machine or the bin, places it over a gauge, it fits, it's a good part. Or we can have a machine checking it. Okay, so that's how that works for us. The 6x dimension with the feature control frame. Refer to the 6x dimension. Where am I? Here we are. Okay. Describe the features and their size dimensions referenced by this. So the reference features are 6 slots. Okay. 0.093 wide. Basic. Interesting. Okay. 2 of the slots are 0.406 long. Right here. With full radius ends, and 4 slots are 0.562 long. With full radius ends. So that's how you would describe the features. It's interesting that it's a size and it is basic. Okay? It's a profile that we're after. The features are controlled by a cylindrical position tolerance of 10 thousandths at MMC relative to datum B, A at max material boundary, and datum C. And we'll get into profile measurement a little later.